In this video, we'll be talking about understanding the reproducibility crisis and its implications. So if you've noticed anything about the reproducibility crisis, which is sometimes called the replication crisis in the news in the last few years, you may have noticed some headlines like this. In Nature News, over half of psychology studies fail reproducibility test. In The Economist, trouble at the lab. Scientists like to think of science as self-correcting. To an alarming degree, it is not. Cancer research is broken from Slate and New America. There's a replication crisis in biomedicine, and no one even knows how deep it runs. In The Week, big science is broken. So what are these headlines about? Well, a number of studies in the last decade have actually attempted to really see how reliable previous scientific findings were in a variety of fields. And the results of these replication studies have been pretty disturbing. So for example, for 100 psychology findings published in top journals, upon repeating the studies, and so these were generally studies that could be repeated using same kind of design, and so there's a collaboration of many psychologists that got together to try to do this to see if they could get the same effects. And only 39% of those studies yielded comparable results. And the mean effect size for those studies actually decreased by about 50% when they were replicated. In other words, the initial studies published much larger effect sizes than the follow-up studies that tried to use the same design to see if they get a similar result. And this is not limited to psychology. In fact, we see the same thing in more laboratory-based sciences. So, for example, Bayer, a large drug company, reported that their in-house drug target validation program could only replicate 20 to 25% of published findings from high-impact journals. And this was out of 67 projects where they had identified potential targets based on, again, good journals with promising findings for potential drugs. But upon trying to just replicate the previously published findings, they found that most could not be replicated, only about 20%. So Amgen also reported successful replication of findings for only 11% of 53 published papers that they tried to replicate findings for in their laboratories. And just another example now from something closer to public health. Among 385 stringent meta-analyses of risk factor association studies for psychiatry, neurology, and somatic diseases, only 48% were consistent with findings from the initial publications. And again, mostly the initial publications had inflated, which in other words is a way of saying larger effect sizes than the studies that came later that tried to replicate them. So looking at these kind of results, it turns out, and even before some of these replication studies were formally available, venture capitalists had already come to believe that the majority of published studies in the scientific literature don't actually have valid findings, even for top journals. Now, why would they think that? And why do we see that borne out when we actually do try to repeat studies? Well, understanding this crisis in reproducibility and its science is really actually quite straightforward now that you've gone through the difficulty of understanding conditional probabilities, hypothesis testing, and statistical power, which are topics we focused on previously in this course and up through this week. So hopefully you have an appreciation by now that when we declare something to be statistically significant, that is not the same thing as saying it's true. Right? So remember, statistical significance is based on a hypothesis test, and we've learned that sometimes we're going to be wrong. We're going to have type 1 or type 2 errors in our conclusions from that hypothesis test. And traditionally, the way we've done these is we've picked a cutoff of 0.05 for the p-value and said associations that we see between exposure and disease or between a risk factor and a health outcome or other ways that we measure effects. But however we measure those point estimates, that when we see an association or an effect with a p-value of less than 0.05, we describe that as statistically significant, and we reject the null hypothesis, right, and say that's a statistically significant association. But all this really means is that the observed data are fairly inconsistent with the null hypothesis. And the null hypothesis, of course, is typically the hypothesis of no effect or treatment of exposure on the health outcome. But recognizing that we are wrong some of the time and thinking about what a p-value means, we have to recognize that there is going to be a certain proportion of the time that we're wrong, and it's not 5%. Remember, the p-value, of course, is the probability of observing data at least as extreme of the sample if the null hypothesis about the population is true. So it's a conditional probability where we're conditioning on the null hypothesis being true. So although that 5% for the p-value is a probability, it's not the probability that we're wrong when we find there is an association, right? Because that would be conditioning on actually observing the association. The p-value conditions on the null hypothesis being true, which is saying that there's no association. Right, so we need to do a little work and think pretty hard about what these probability means if we want to think about the probability, say, that we're wrong when we do see an association. Okay, so let's think about that a little more carefully. And it turns out there's a nice guide to doing that. This was published actually decades ago in an epidemiology journal. And I believe this is one of your required readings for this week. It's a good paper. Go take a look at it if you haven't already. But the idea of this paper is to actually use the framework you're already familiar with about sensitivity, specificity, positive and negative predictive values, and apply it to now thinking about every kind of study that we do looking at an exposure disease association or risk factor disease association. Every one of those studies, or really even sometimes we have multiple analyses within a single paper, within a single study, but every one of those analyses where we're running a statistical test, a hypothesis test, we can consider the hypothesis test itself as an imperfect diagnostic test that has some sensitivity, some specificity, and some positive and negative predictive value. All right, so for example, we can consider a case control study, which is one type of association study. And remember that any of these studies are using samples to make inferences about the target population from which we're taking the sample. Right? And so we're going to declare an association statistically significant, which you can think of as test positive in our imperfect diagnostic test framework. Right? Because of course we know that we have an imperfect test. Sometimes we'll have a type 1 error, sometimes we'll have a type 2 error, sometimes we'll get it right. Right? But we're going to declare an association statistically significant with this test, the hypothesis test, if our confidence interval excludes the null hypothesis, such as an odds ratio of 1, or if the p-value is less than alpha, where typically, of course, by tradition, we're using 0.05 or 5% for alpha. Right, so in thinking about this framework, of course, if declaring an association as statistically significant is testing positive on our imperfect test, then testing negative would be a lack of statistical significance, right, where we fail to reject the null hypothesis. Okay, now recognizing, of course, that this test is imperfect, we also need to think about whether that association actually exists in the target population, because of course we can see whether it exists in our sample, but we're using a hypothesis test or a confidence interval to determine whether we think that is likely to also exist in the target population that we sampled from. In other words, whether it's statistically significant. All right, so let's think about now some notation for whether that exposure disease association truly exists in the population. So we call that D plus for disease plus. And again, here we're thinking in this situation is not like an actual disease, but D plus is just our notation for whether that risk factor or exposure disease association actually exists in the population. And then D minus would be that there's not a true association. Okay, so once we have this notation, we should recognize that actually some of the concepts we've been talking about already, like power and type 1 error rates, are actually just, again, related to these concepts of sensitivity and specificity that we've talked about in epidemiology and also earlier in this class. So for example, if there's no confounding or other bias, then statistical power, I recall that power is just the probability of rejecting the null hypothesis, given that the null hypothesis is false. right? So if the null hypothesis is false, there really is a true association between the risk factor and disease. And if we reject the null hypothesis, then we're declaring there's a significant or statistically significant association or result. Right? So power is therefore just the probability of getting a significant result, statistical significance, given that there is a true association there. Right? So in our notation, that's just the probability of testing positive on our hypothesis test, given D positive, that there really is an association there. Well, of course, probability of T plus given D plus is just the sensitivity. Right? So we can think of this as the sensitivity of the study and our statistical analysis, our hypothesis test, for detecting a true association. The type 1 error rate, which again is alpha, is just the probability of getting a significant result, right, of seeing statistical significance, given that we do not have a true association. Right? And of course that is an error because here we don't have an association, but we declare that we have evidence of one, that we have statistical significance. Okay, and so in our notation, that's probability of T plus given D minus, and recognizing, of course, that that's not specificity, but it's the complement of specificity because, again, if we condition on the same thing, on D minus, then those conditional complements, those probabilities have to add to 1. So we can just write that the type 1 error rate is 1 minus the specificity of our hypothesis test. Finally, we have the positive predictive value, right, which is the probability that we have a true disease association given that we have a significant result. Right? And this is actually what we want to condition on if we want to think about the reliability of published studies and published findings. Because in that setting, what we're doing is saying, well, I've got this paper, it says there's statistical significance. Given that that's true, we're conditioning on that being true, what is the probability of actually there being a real association between the risk factor and disease in the population? Right? So we clearly want to sort of flip around, as we've done here with positive predictive value, the conditional order in order to think about the reliability of published results. Right? So, of course, in our notation, that's just the probability of D plus given T plus, and we know how to get that. Right? This is just a standard textbook formula. You've learned it in the epidemiology course. You also, now in this course, have learned how to calculate it using Bayes' rule. And of course, in our notation now, we're thinking again of sensitivity, specificity of our hypothesis test, right, which we've said, okay, sensitivity is just the same thing as the power of the test. And 1 minus specificity, of course, is alpha, so specificity is 1 minus alpha. And so we could substitute any of those into the formula. And we see at the bottom of the screen then, when we substitute that, exactly that we end up with this formula for positive predictive value and its relationship to statistical power, to alpha, and to the prevalence of the true disease associations. And let's talk about that a little more. So what does that mean, the prevalence of true disease associations or exposure disease associations among those tested? So what we have to do to think about this parameter, the prevalence, is really think about the population of all the tests, all the hypothesis tests we run in science, right? And so if it's helpful, you can think of that as maybe thinking about one field at a time. So for example, in clinical trials, only about 9.6% of investigational drugs make it from phase 1, which is the first step in the clinical trial process, to actually getting FDA approval. Right, so that might be one example of a way to think about the prevalence of true associations. If you assume that FDA approval only comes when you've actually got pretty good evidence that a drug actually truly impacts and improves the disease or cures the disease, then you might think of that 9.6 or about 10% as an estimate of the prevalence of true associations between drugs and positive effects out of a population where of a larger population of drugs that are being tested. Right? So for that example, we would say prevalence is 0.096, power is 0.90. Why 0.90? Well, typically in most of these clinical trials and in as well as our investigational studies in epidemiology, we try to shoot for very high power. Try to design a study with a large enough sample size that will have at least 80 or 90% power. Right? So 90% would be a pretty good target that would be pretty typical to try to get to, and then figuring out how many subjects you would actually need for a study to have reasonable results and reasonable power. And of course, alpha of 0.05, again, is a tradition across the sciences. And so if you plug in those values into the positive predictive value formula, you see that you actually only get about 66% for the positive predictive value. In other words, you would expect for a population of studies all done with 90% power for new investigational drugs, that only 66% of the statistically significant results from those studies would actually reflect drugs that really work. Right? So of course that's much lower than the power because we've got a completely different probability. Remember, the power, if we go back to the previous slide, is probability of t plus given d plus. The positive predictive value, though, is probability of d plus given t plus. Right? So of course they're different values here. And what's a little surprising to people until they actually sit down and take the time to do these kind of calculations is how much lower the positive predictive value is than the power. Okay, so that gives you some sense of why maybe a number of findings wouldn't be really reliable, but it's also important to understand that in a lot of the sciences, we may not even have this optimistic situation as in the first calculation with 90% power. In fact, it's not unusual in real public health studies to see secondary aims and post hoc analyses. Post hoc analyses are just analyses you've done sort of after the fact. They weren't necessarily part of your original plan, but you get the data, you start looking at it, you see some interesting patterns, and maybe you run some additional statistical tests. Well, these kind of aims, secondary aims and post hoc analyses, are often not planned in advance, and so they're often underpowered. We haven't designed the study to be sure that we have enough samples, enough of a sample size to actually get reliable results. And so because of that, it's been estimated that actually the average power for all published medical literature may be anywhere from 20 to 50%. And so if we use 50%, which is somewhat optimistic, I think, and again the 9.6% prevalence for the prevalence of true associations among all the statistical tests that get run, then we would see the positive predictive value drop pretty quickly to now 52% for alpha of 0.05, which is traditional. I actually saw a talk at a conference, an epidemiology conference, several years ago, where someone actually had an underpowered a secondary aim that they knew wouldn't have a lot of power, and they had actually been taught to use a more relaxed value of alpha, a higher value of alpha for the type 1 error rate to do that. And I think that's just absolutely the wrong thing to do. I would never advise you to do that because, in fact, what you see is that makes this problem of the reliability even worse. So, for example, you increase alpha to 0.2 and allow that type 1 error rate to be 20% instead of 5%. The positive predictive value drops to only 21%. So, in fact, only about 1 in 5 is 20%. Only about 1 in 5 of your statistically significant findings would actually reflect two results if you actually use that higher value of alpha. Another important point here is that accounting for bias, and we haven't even talked about bias yet, right? We've assumed actually that we have a perfectly unbiased study right now. So we've got perfect control of confounding. We don't have any sort of selective reporting when we look at published findings, that there's no sort of data dredging or other activities that lead to biased findings. So if we have perfectly conducted studies that just happen to have low power, then the above calculations make sense. But as soon as we start thinking about potential biases, then that will tend to drop our positive predictive value even further. And so Unitas, in a very heavily cited paper, has argued that that bias easily gets us down below 50% for the positive predictive value, which would mean, of course, if it's less than 50% positive predictive value, then it's more likely than not that a statistically significant result that we pull at random from the literature would actually be meaningless, wouldn't reflect a real association in the population or a real effect of a drug or a real effect of a risk factor on disease.